Hello and welcome back to EGR 151 Electrical Machinery. In this unit, we'll be talking about series circuits. And specifically, we'll be looking at resistors in series. But keep in mind, just about any component can be installed in a circuit in series, just that we've just started with resistors, so it's not just limited to that. So what are we trying to accomplish in this unit? Well, it turns out we want you to be familiar with series circuits. So you need to understand the various properties of series circuits, essentially how they're put together. Then you need to be able to analyze them. So quantities like resistance, current, voltage, power, those are all things you're going to be able to need to calculate. To do that, it turns out there are sets of rules that are associated with series circuits, so we need to know those and how to use them. Another aspect is series circuits are usually designed to create changes in voltage, so we need to be familiar with the concept of voltage drop and be able to use the voltage divider formula to calculate the various voltage drops. So before we discuss series circuits, you should understand that electrical circuits can be configured in different ways. They can be broken down into three major categories or types. We have series circuits, where essentially things are on a line. We have parallel circuits, where there are multiple lines or multiple paths. And of course, we have combinations of those. And that's where some of the components are in series, some of the components are in parallel. And that's true of most complicated pieces of equipment or complicated circuits, because there's a lot more going on than could just be seen in a series or parallel circuit. So let's start with series circuits. And it turns out that what makes it a series circuits is essentially all of the components are installed in series. So as a result, there's essentially only one path through the circuit. If you take a look, our example here, you can see it starts out currents flowing out of the negative side of our battery. It's going to go through resistor 1, resistor 2, resistor 3, resistor 4, resistor 5, and back to the battery. So there's only one path, and essentially all the current has to go through each of these various components. All right, so that's what makes something a series circuit. Now, an example of a series circuit that most people are familiar with is essentially any circuit that includes a fuse or a circuit breaker. So for example, we'll take a look at this one down here. We have a DC motor. We have some form of generator over here. We're not defining that. That could be a battery, that could be a power supply. And in terms of our current flowing out, all of our current is going to flow through this fuse. Now, the whole idea of fuses and circuit breakers, that if for some reason they're activated, right, blown a fuse or popped a circuit breaker, they will stop all the current. As a result, they must be in series, so all the current has to go through them, right? So essentially, then we know if the fuse opens or the circuit breaker pops, it's going to disconnect the entire circuit. So that's a simple example of components being mounted in series. In this case, the fuse is essentially a type of resistor, and then a DC motor, another type of component we'll talk more about down the road later in the semester. Another important aspect of series circuits is that they call voltage drops. So if we take a look, we're going to have a battery. The battery is going to have a certain voltage. And what we're going to see is that there's going to be a voltage drop across each of these resistors. So one voltage drop, another voltage drop, another voltage drop, another voltage drop. And it turns out that the total of the voltage drops across all of these circuits, or I should say all of these components, is going to be equal to the applied voltage, in this case coming from the battery. All right, so if you could sum these up, measure these and sum these up, they're going to give you a total for the total voltage applied to this circuit. For example, let's take a look at this circuit. We have a 20 volt DC power supply, and it's going to go across 1, 2, 3, 4 resistors. This is a 10 ohm resistor. This is a slightly larger 14 ohm resistor, 16 ohm resistor, and then a smaller 8 ohm resistor. And you'll see across the 10 ohm resistor, we have 5 volts DC. We then have 7 volts DC. Across the 16, 8 volts DC. Across the 8, 4 volts DC, you can probably see pretty clearly that the voltage drops are proportional to the resistance. The other thing you can probably see is that if we were to add these up, 5 plus 7 plus 8 plus 4, that would of course equal 24 volts DC. Right? So each of these voltage drops, when summed, is going to be equal to the total applied voltage. So how do we figure out what those values are? Well, it turns out the first thing you need to know is what is the total resistance in the series circuit. And the key thing about this is because we only have one path, right? The current has to flow through each of the various resistors, and each of those resistors is going to limit the amount of current flow. It's going to resist that current flow. The more resistance you have, the lower the current flow is going to be. As a result, the total amount of resistance is just going to be equal to the sum. So we would just add the resistance up of the resistors in series, and whatever their total resistance is, of course in ohms, you would get the total resistance for the circuit. Pretty straightforward. Now, a couple things that are important to keep in mind when you're calculating the various values associated with circuits is these 3 rules. One, the current's going to be the same at any point in the circuit. So the current coming out of the power supply is going to be the same going through 1, 2, 3, 4 of many resistors you have in circuit and back. The total resistance is going to be the sum of those resistance. You can just add them up. And then, of course, the applied voltage is going to be equal to the sum of all the voltage drops, right? So we looked at that one where it was 24 volts applied, and then what was it, 5, 7, 8, 10. It's got to add up to the total value of 24. So here are the various formulas that go along with those rules. So as I said, the total resistance is just going to be the sum of the resistance. So in this case here, the total resistance of the circuit would just be resistor 1 value plus resistor 2, resistor 3, etc., out to as many resistors as you have in series. Of course, resistance is measured in ohms. And if we want to calculate the current flow, our total current flow is just going to be equal to our total voltage or our applied voltage divided by our total resistance. Right? And if we were to take a look at that, keep in mind this is just a manipulation of the Ohm's law, right? Ohm's law is that E voltage is going to be equal to IR, current times resistance. Just manipulating that equation around a simple algebraic manipulation to solve for our total current. Again, the current is going to be the same throughout the system. So if you've calculated a total current flow, that's going to be the same as the current flow in each of the resistors. So I1s, I2, I3, same throughout. And then if you want to calculate the voltage drop across an actual individual resistor, you could then calculate the voltage, again, using Ohm's law, that it's the current flowing through I1, again, same as total current, multiplied by the resistance, in this case, the first resistor. Now, these formulas definitely require memorization. Right? You need to know how to use these and need to apply them. And I recommend that if you have a place where you're planning on keeping formulas, some type of formula sheet or formula record, this is a good place, a good set of formulas to add to that. We're going to have ones for series circuits, parallel circuits, combination circuits, etc. And we will have a lot of formulas to work with. So developing an organizational scheme for this would definitely be helpful. So let's go through and do a quick example. So in this case here, we want to find the voltage drop across all the resistors. It turns out that we can find that by just adding them up, right? So in this case here, if the voltage drop is 40 volts across this first resistor, 20 volts across the second resistor, and 60 volts across this third resistor, right? Remember, you can say that, show clearly that the resistance is going to be proportional to the voltage drop. So a 20 ohm resistor causes a 40 volt drop, a 10 ohm resistance only causes a 20 volt drop, and the 30 ohm resistance causes a 60 volt drop. And of course, the constant here is the current, 2 amps through 1, 2 amps through 2, 2 amps through 3. And if you just add those up, 40 plus 20 plus 60, that's going to equal 120. Right, so essentially we know that each of these is going to have same current, and the total voltage drop across all of them is just going to be the sum of the voltage drops. Now, oftentimes series circuits are used as voltage dividers. So you're given a voltage, a total voltage, but you may want different voltages for different parts of the circuits. So by putting in different resistances, right, we can get different voltage drops. Right, so in our case here, this is going to be at essentially 0 coming out, depending on where you define ground as, and then this is going to go up 20, up 30, up 50, up 100 to come back to 200 on this other side. So 20 plus 30 plus 50, 100 equals 200. So when combined together, these are referred as the general voltage divider formula, right? And in terms of this, we can use this formula to determine the voltage drops, right? So again, we go through and determine our total current, right? In this case, remember that our total current is going to be equal to our total voltage divided by our total resistance, right? In terms of the voltage drops across any of the individual resistors, you then would take this total current, right? Because keep in mind the total current is going to be the same as the current in any one spot, multiply it by the resistance of that individual resistor, and that will tell you what the voltage drop is, right? So you could calculate these individually, or you could go through and sum them potentially to determine the total drop, etc. So a bunch of different uses for this formula. Keep in mind, again, this is an application of Ohm's law. Keep in mind that if we were looking again at the individual voltage, we know that the total current is just going to be equal to the total voltage divided by the total resistance. And of course, the total current multiplied by R sub X, whatever our resistance is going to give our voltage drop. We can bypass one step then if we want to find the formula, the voltage drop in an individual circuit. We don't have to solve for the current first. We can just use the resistance, right, compared to the total resistance. Keep in mind that voltage drop is going to be proportional to the resistance and multiply it by our total applied voltage, E sub t. Right, so each of these can be done just using the resistance values if you want to avoid the step of calculating current. So just like many other technical quantities, you need to have a sign convention, essentially what's considered positive, what's considered negative. And with electrical equipment, this is going to be governed by polarity. So in terms of what do we defined as the positive and negative polarity, and what does that represent? Well, you can usually determine it by observing it and particularly looking at the current flow. Keep in mind the current is always going to be shown as flowing out of the negative terminal, right? And it's going to flow through and around to the positive terminal. Right, so in terms of our sources, here's going to be our current flow. It's going to essentially flow from a lower point up to a positive point. Oftentimes our lower point is defined as 0. So for example, we'd start at 0, go to plus 20 volts. We would then go from 20 to 50 volts, right? Because the difference here is 30. We would then go from 50 to 100, again a difference of 50, and then go from 100 to 200 to come up with the total amount, right? So this is all going to be relative to some 0 point. So we do need to define what is that 0 point, right? So what do we say is 0? And that's defined by the ground, right? So whatever we define as the ground is going to be a reference point. Keep in mind we can have the ground tied directly to the earth, right? That's the symbol for this. Or another common thing that happens in electrical equipment is it's going to all be tied to the chassis, right? The chassis itself is grounded, so if there's any shorts or anything like that, the chassis can't be energized, so it's a safety procedure. So oftentimes all of our grounds is going to be tied to a chassis ground. And so this is, of course, just a reference. As with sign conventions, you could switch them around, but this is pretty much a pretty set in stone set of points in terms of our sign convention. So it's pretty universal. Clearly, there might be times where changing your sign convention might be helpful. We'll get into a few of those during the semester, but by far, pretty much always when we talk about polarity and ground is 0, etc., that's going to be the standard rule. So how would this polarity show up in our meters? So for example, here we have a simple gauge for measuring voltage. You see it's tied to ground, right? Both these are tied to ground. You notice actually there's 1, 2, 3, 4 ground symbols here. Don't be confused. This is just to make the diagram simpler. These are all the same ground, right? So this is all tied to earth. That would be generally your 0 point. So just because you see multiple ground symbols doesn't mean there's multiple grounds. It's just a convention used to keep diagrams simple. So here we go. We have 2 batteries, very likely, and in this case here we have voltage tied together. Current's going to flow out of here, right? And so it turns out that this is going to be below ground, right? Not really below ground, literally, but it's going to be lower than ground. And if you come up here and look at the voltmeter is showing it as a negative voltage. Okay, this would take it up to ground going across this resistor. All right, going over here, same basic setup. Now we're going from ground up to a positive voltage. Right, the voltage here and the voltage here are the same. It's going to be 12 volts. It's going to be above ground. Right, so that's how it's kind of shown up. It's just essentially a sign convention. We could have set it up in the opposite direction, but this is the standard sign convention, and in terms of this, you need to keep this in mind when you're showing voltages relative to ground. So to summarize, this is what we know about series circuits, right? There is only one path of flow. Right, that's essentially what makes them a series circuit. As a result, the current is going to be the same at any point, right? Same flow through each of the resistors, if those example or any other component in series. Turns out that if we want to find out what the total resistance is, we can just add up the individual resistors, right, if they're in series. And if we want to determine the total voltage, in this case the applied voltage, it's just going to be equal to the sum of the individual voltage drops, right? So it's going to be the drops across each of the components in our example's resistors. An example of a series circuit is any circuit that has a fuse or a circuit breaker. They must be connected in series because of the way we want them to function. If that fuse is blown or the circuit breaker is activated, we want to make sure that no current can flow to the device, so it's protected. In general, the whole idea of these is protect them from higher voltages or higher currents than they are able to withstand. We haven't really mentioned power too much. We'll get into that, but it's pretty straightforward that the total power in any circuit, right, is just going to be equal to the sum of the power, right? So if resistors are dissipating multiple volts of power, you want to determine the total power, you would just add them up. And by the way, that really doesn't matter whether we're talking about series circuits or parallel circuits or combination circuits for that matter. The total power used by a circuit is going to be equal to the sum of the power of the power used or dissipated by all the various components and parts. Right, so now if we have a known voltage and we have total resistance, we can go through and calculate it. You can use the general voltage divider formula, right? That's a quick way to determine voltage drops without having to go through all the multiple steps of determining current, etc. Because it turns out that the voltage drop is going to be equal to, or should be the ratio of the voltage drop to the source voltage is going to be equal to the individual resistance to the total resistance, right? So it's a pretty straightforward ratio. So that wraps up our conversation about series circuits. As always, take advantage of your textbook and the additional resources on the course space to further your understanding. And as always, if you have any questions, don't hesitate to get in touch with me.